Good afternoon. We are the Group 13, presenting our final data science project. For this data science project, we carefully analyzed and followed the step-by-step processes of this project, and we are willing to share our experiences and steps on how we cleansed our data. The first step is data gathering. For our data gathering, we decided to use a dataset from the internet that finds a balance between simplicity and complexity. The instructions stated that the data should be obtained from Kaggle or a similar platform that provides broad and unbiased datasets. After reviewing the multiple datasets accessible on various websites, we ultimately decided on an airline safety dataset obtained from GitHub. This Python code is part of a data science project and is focused on data gathering. Let's break down the code step by step. First is we imported the necessary libraries for our code. Pandas is imported for data manipulation using data frames. NumPy is imported for numerical operations. Matplotlib.pylot, pyplot, and Seaborn are imported for data visualization. Google.colab.files is imported for uploading files from the local machine to Google Colab. Second is we uploaded the data files needed for our processes. The files that upload function from Google Colab is used to upload files from the local machine to the Colab environment. Third is reading CSV file into Pandas data frame. This code reads a CSV files named airline safety.csv into a Pandas data frame named airline underscore safety. This assumes that the CSV is uploaded using the file dialog in the previous step. The pd.read CSV function is used to read the CSV file into the data frame, making it ready for further analysis and manipulation. In summary, this code snippet sets up the environment for a data science project by importing necessary libraries, facilitates file upload from the local machine to Google Colab, and reads a specific CSV file into a Pandas data frame for subsequent analysis. Now, let us move on to the next step of our project, data cleansing of our collected data. In the upcoming phase of our project, we need to perform the data cleansing, which involves removing unnecessary columns from our dataset. This step is crucial as it streamlines the data for subsequent processes and facilitates better organization. In our current dataset, column labeled fatal accidents 85 to 99 and fatal accidents 00 to 14, our data refinement emphasizes a strategic focus on occurrences rather than fatal accidents to highlight preventive actions and safety advancements, since an airline safety measures the safety evaluation of an airline company. While accidents, which are frequently caused by a human mistake, have serious consequences, doesn't have much relevancy within the data, whereas incidents that show possible safety gaps or non-fatal difficulties, which highlight the context of airline safety and showcase the overall efficiency and clarity of our dataset by removing the irrelevant columns. This data cleansing code is focused on preparing the airline safety data frame for analysis by removing certain columns. Let's break down this step by step. First is we display the column names. This line simply displays the column names of airline safety data frame. It's a quick way to inspect the structure of data frame and see what columns are present. Next is we remove the specified columns. Airline safety equals airline safety.drop, columns equals columns to remove is creating a list of names, columns to remove containing the names of columns that needs to be removed. The drop method is when you use on the airline safety data frame to remove this specified columns, then modified data frame is assigned back to the variable airline safety. Lastly is we display the head of the data frame. This line prints the first few rows of the modified data frame using the head method. It allows a quick visual check to ensure that specified columns have been successfully removed. In summary, this data cleansing code removes specific columns from the airline safety data frame, providing a cleaner and more focused dataset for subsequent analysis in the data science project. The decision to remove these columns is based on the project's requirements and the need to focus on relevant information.
Moving on, we're diving into the third phase of our project, where we embark on the explanatory data analysis, also known as the ADA, to analyze the dataset on airline safety and evaluate the historical changes in airline safety incidents, which is one of the objectives of our project. Furthermore, we have these three questions for our problem statement that needs to be answered, which is going to be answered at the end of our project. First is how was the number of incidents changed over the time of these airlines? Second is there a correlation between a certain metrics such as available seat kilometers and incidents or fatality rate? Or are there any observable patterns or shifts in the fatalities recorded across the different years during the periods of 1985 to 1999 and 2000 to 2004? So to find that out, let's start getting an overview of our data set. First, let's start with the shape, descriptive statistics, and information. Some other information that we're going to cover. We have the airline safety dot shapes, which this command's purpose is to break the shape of the data set, indicating the number of rows and columns. And then we initialize the airline safety describe, which provides a descriptive statistics for the numerical columns in the airline safety data frame. And then we have the airline safety info, which displays the general information about the data set, including the data types and non-null counts on our ETA. And to clarify, these commands will provide an insights into the size of our data sets because it will show the statistical summary on the data types that are involved. Now, data. Next is the data inference or correlation. We sort the data frame from available kilometers column to ascending. As you can see, all of that from available kilometers per week up to the fatalities of 2000 to 2014 are in the column of ascending order and it only display the first few rows. Moving on, we're going now to the calculation of correlation matrix for the entire dataset, or also known as the correlation analysis. Correlation matrix calculates the correlation matrix is used to calculate the entire data set, and we now initialize the significant variables. Sort variables by correlation with like the available seat kilometers per week. And we're going to print them just like here. And here's the data, the result of the statistics itself. And next is displaying the variables sorted by the correlation with the available seat kilometers per week. And after that, we print it out just like what we did from the correlation matrix. And these statistics are part of the selected features, which is contributing to our overall analysis. Now, moving on to the descriptive statistics. Moving on to the correlation with the descriptive statistics for selected features. And here in the selected features, it calculates the descriptive statistics for selected features. As you can see, the available seat kilometers incidents from 85 to 99 and incidents from 2000 to 2014 and fatalities from 1985 to 1999 are here in the correlation, the available seat per week. And also, we're now moving on to the bar graphs, or also known as the visualizations of our overall BPE. First, we have the airline for 1985, and here we create the bar plot for it by initializing the SNS bar plot, and then set the plot, the titles, and other labels as well. And as you can see, we have the top 10 airlines by incidents where we display it, and it just showed that the highest fatality or number of incidents is around 70 during the 1985 up to 1999. And then we have the bar, bar graph for the 2000 to 2014 with the number of incidents to 25. As you can see, it has reduced by about. Although the other air, airport or airline has increased, it has reduced the numbers of incidents due to some different factors. And then we're moving on now to the scatter plot, where we're going to make sure that here we can see that the title, the label as well, and this shows the relationship with the kilometers and fatalities from 1985 to 1999. Similar here, but it is in the year of 2000 to 2014. Finally, we're going to the correlation between available seat kilometers and incidents. And here we display the correlation between metrics. So what does that do? The correlation between the metrics is between the available seat kilometers and incident fatality rates. For the subplots for incidents and fatalities by airline, in here, as you can see, these subplots provide a comprehensive comparison of incidents and fatalities by airline for the very specific time periods. And that's it for our exclamatory data analysis.
Next step we have is the data modeling process. We start by using the random forest regressor model for accurate data prediction. Employing the ensemble learning technique. To enhance the model's robustness, we apply skits-learn's standard scaler to standardize features and mitigate scale differences. The dataset is then split into training and testing sets using the train test split function, enabling evaluation on the new data. Mean squared error is used as a metric for model evaluation, measuring the average squared difference between predicted and actual values. Pandas is utilized for efficient data manipulation, and the I/O module handles the input-output task. These modules collectively form a robust data modeling strategy. As we can see here in the um, as we can see here in our Python, we use the skits ensemble to import the random forest regression, and then we input the standard scaler. Then we input the train test split for data splitting, which means we import mean squared error for model evaluation. And then lastly, we input the I/O for handling the input and output operations. Then we use the airline underscore safety dot head function to display the few first rows of the airline safety dataset to inspect the structure and contents as shown here. Then we select the features and target variables for each data. Next, we print out the airline safety, where it shows that the airline Next, we separate the features and target variables as shown here. Then we split the data into the training datasets. Next, we create the data frame for the training dataset, and then we create the data frame for the test dataset. Next, we display the first few rows of the training dataset, then the first few rows of the training. Then we display the first. Then we check for the missing values in the training dataset, as shown here. Next, we set up the matplotlib figure. Then we initialize the scaler. We then fit the scaler onto the training data and then transfer both into training and testing data. Then the random forest regression model has been initialized, and then thus we can train the model. We can create a prediction on the scaled testing data, and then we can then calculate for the mean square error. We can then visualize the actual versus predicted values using the scatter plot as shown here in the plot figurine here. Nextly, we calculate the feature importances using the train random forest regression model. The importances variable stores the calculated importance for each feature. Then this features variable contains the names of the features used in this model. Next, we plot the feature importance. Then we can visualize the feature importance in a bar plot as shown here.
Lastly, we have evaluation. In data science, evaluation is the process of assessing the performance of a machine learning model. This process is crucial to ensure that the model generalizes well and reduces the error rate for future predictions. When evaluating the performance of a regression model, one can use several metrics. To begin with, the mean absolute error, or MAE, calculates the average absolute difference between predicted and actual values. Then, the R squared score measures how well the model explains the variance in the target variable. The residual analysis can help understand the distribution and patterns of errors. Moreover, cross-validation is used to provide a more robust assessment of model performance. By using cross-val score to perform five-fold cross-validation on the random forest model, negative mean squared error, or MSE, can be calculated for each fold. Consequently, the root mean squared error, or RMSE, can be computed across folds by taking the square root of the negative MSE values. As a result, displaying the cross-validated MSE for each fold can help evaluate model performance during cross-validation. The mean RMSE across all folds provides a consolidated measure of model performance through cross-validation. Now, to assess the model's performance on unseen data, predictions are generated on a separate holdout dataset using the trained random forest model. As a result, the mean squared error, or MSE, on the holdout set calculates and prints to evaluate the model's performance on unseen data.
To answer our three problems, Eric, here's the answers to our problem statement. How has the number of events varied throughout the years from 1985 to 1999 and 2000 to 2014? And are there any obvious trends? According to the bar graphs, the numbers of occurrences for various airlines has changed significantly between 1985 and 1999, as well as 2000 and 2014. The airlines with the most occurrences between 1985 and 1999 were Aeroflot, China Airlines, Egyptier, Avianca, Ethiopian Airlines, Kenya Airways, PIA, and AN, Indian Airlines, and Air France. Notably, Aeroflot had the highest incident count among them, showing a poorly safety record during this time period. In contrast, from 2000 to 2014, Delta, North or Northwest American, United, United Central, US Airways, American West Stam, Brazil, Air France, Air, Air France Go Brazil, Korean Air Runner, Turkish Airlines had the most incidents. Delta Northwest had the highest number of events throughout this period. Comparison to the two periods demonstrates considerable changes in the rankings. For example, Aeroflot, which had led in occurrences from 1985 to 1999, did not even crack the top 10 in the 2000 to 2014 period. Delta, Delta or Northwest, which led in occurrences 2000 to 2014, did not appear in the top 10 from 1985 to 1999. This shows that this airline safety performance will evolve over time. Some airline safety records have clearly improved, but others have been swings in an important and increase in mishaps. For our number two, is there a correlation between certain metrics and the incidence rate fatalities? Based on the table, it appears that there is a link between available seat kilometers and incident or fatalities. The image correlation metrics reveal positive connections between available seat kilometers per week and incidents from 1985 to 1999, incidents from 2000 to 2014, fatalities from 1985 to 1999, and fatalities from 2000 to 2014. While the correlation coefficients are not near one, they do suggest to moderately positively. This shows that as the available seat kilometers per week increase, so do the amount of incidents and fatalities. For the number three, other observable patterns or the shifts in the fatalities recorded across from the years during the periods of 1985 to 1999 and 2000 to 2014. From earlier, the graphs reveal distinct patterns and shifts in the reported fatalities across different years during the periods of 1985 to 1990 and 2000 to 2014. In the earlier time frame, fatalities were generally higher, indicating a more challenging year for airline safety and several airlines experiencing significant casualties. Conversely, the 2000 to 2014 period demonstrated a noticeably reduction in fatalities for most airlines. Despite occasional spikes, this overall trend points to decrease in fatal incidents, suggesting an improvement in airline safety over the years. The positive shift could be attributed to various factors such as advancement in aviation technology, enhanced safety regulations, and heightened focus on training and safety culture within the airlines industry. These insights contribute to a comprehensive evaluation of historical changes in airline and safety incidents. For our recommendation, future, future studies should go further into the information, looking for additional indicators such as keywords, release dates, and aviation authority engagement to acquire more complete knowledge of the elements influencing airline safety. Industry stakeholders and future researchers are encouraged to use statistical insights to guide decisions and proactively improve safety measures. Regular reviews and adjustment of safety standards based on the evolving trends can help to reduce incidents and fatalities. The demonstrated usage of machine learning and models implies that they have potential in predictive analytics for anticipating safety events, which can benefit in the formulation of proactive plans and resource allocation. Incorporating such as technical improvements into safety management systems could be critical to ensuring a safe aviation environment. And here are our references. And as we conclude this discussion, it is crucial for stakeholders and other researchers that will use this data to remain vigilant, adaptive, and committed to continuous improvement. and to ensure safe and reliable aviation environment for the future.